Yeah.
I completely vanished all the way to
got
red.
two more.
Okay. So that explains that. Molly, I recommend you give yourself some water to drink during it. Oh my God, right.
They might be hard to understand.
Ryan, you want me to grab you some water on that?
Sure.
Might need more than that for the skills saturated. I said might need more than that to keep the skills saturated.
We didn't have a chance to go up and to take advantage of that.
Volume or affair.
Thanks, I got it. I haven't heard that one before.
I know all about completely creative.
What's the time this morning?
This morning?
Yeah. I was talking that much in another time. Allergies don't help.
There's a reason your professor is stuck on cough drops for the first week and a half of the semester.
What?
I said there's a reason we suck on cough drops the first 2 weeks of the semester.
When do we find out if we pass?
Try again.
Has anyone has yet failed?
Yes, we know someone who failed.
No, today.
Oh, today.
Wait, who failed?
I've only had 2/3 of mine go. I don't know how Alan's grading anything.
You probably failed me. I'm not graduating.
Just had to bring that up right before.
I was wondering, like, when do we find out? When do we find out if we're graduating?
What did you bus? Oh, bus.
It's memories. This is why I locked my computer around you.
Yes, because I will make notepad documents full of the word box over and over.
Oh, it was bus.
How horribly malicious of me.
I know.
Alan would like you to know that you will find out your grades for SMP when grades are released.
But we have to walk to graduation before that, so that's the
Mm-mm.
point. I mean, I'm not
No,
even asking for
I
grades.
promise, if you're not walking at graduation, someone will let you know.
But by when?
By the time
Or,
you get there.
here's what Alan says, or when they get an email from the registrar sometime after Tuesday.
Tuesday.
On the afternoon, 7 days from today.
Okay.
Yeah, that's when our grades
No, I just didn't.
are due for you guys.
Okay.
So,
Can I have a drink?
So,
I guess we're
hold on.
right. So I'm
Okay.
Ryan Wilson. My mentor for this was Dr. Lindsay Jameson, and I worked with planning and optimization with 2-3 dominating sets. First thing we look at is what is domination for those who wouldn't know. Basically, you have some sort of graph, G, and it is a graph that contains a certain amount of vertices and a certain amount of edges, and they're all connected in some way. Dominating set on the graph would be some set where every node that is not in the set, or every vertex that's not in the set, would be adjacent to a vertex that is in the set. And we can also say that the node is one away from all of these other nodes. Some of the background into domination as a whole, basically, one thing a long time ago was 1862, the n queens problem. They were trying to find optimal solutions to place queens on a board, and it relates to domination in some ways because you're trying to find an optimum solution to the amount that you can have on there. Some aspects that were introduced in the 1950s and 60s were terms, or not terms, but the idea of a dominating set and domination number. The actual terms weren't actually brought into local use until 1962. And then they started to, in 1972, they actually came with a shorthand notation, which would be gamma G, which would be the domination number in a graph. And also in the 1990s, we found a few different sources that talk about common K domination. So it's not just where the nodes are 1 away; they could be K away, and so you might have a 3 dominating set or 4 dominating set, or something of the like. The first instance of secondary domination, however, was not until 2008. There was a paper by Ednami, Nisley, and Rawl in 2008 that discussed this, and they went into a 1K dominating set. That's what they talked about mainly, and it was so you have 2 guards, and first one of the guards on the nodes would be adjacent to the nodes not in the set, and the other one would be a certain distance away, just like in K domination. There was also a more general form of this, which is MN dominating sets, and this was talked a little more in a paper by Jameson in 2009, and it's just a more generalized form. So one of the nodes is M away, and the other one is N away. Just some quick definitions. Dominating set where every vertex not in the set is adjacent or 1 away from a node in the set. So that's the dominating set definition I gave you earlier. And the domination number is the number of elements contained in the set, or the cardinality of the set. Here's some examples of different dominating sets on graphs. And the first one is just the one I showed before, and it's just a standard dominating set. The second one is the next two are more K domination. So in the second one here, you can see that it takes 4 moves to be able to get to the final node over here, and so this will be a 4 dominating set. And then this one's just to show that even if it's different on both sides, still the maximum distance this one would have to travel would be 3, so it would still be a 3 dominating set. Secondary domination I went into a little before. Basically our definition for that is so where every vertex not in the set is adjacent to a vertex in the set, and the next closest vertex is K away. And this is strictly for 1K dominating sets, not for the general term. If we go into the general definition, we have the one I stated earlier, where the closest guard is M away, and the second closest guard is N away from this is the maximum distance. We can also, the way we would say this is we have an MN dominating set on a graph G. Given a graph G and a set S on G, we need to know also how to find M and N though. So here are just some examples of secondary dominating sets on different graphs. These are both paths, of course, and mainly I'll be looking at paths here. Basically, we have up here a 2-3 dominating set. The closest node, maximum distance that this node would have to travel would be 2, and the maximum would have to travel is 3. And so you end up having a 2-3 dominating set on this path, P4. And this one here is a little bit different. The maximum distance that the closest node would ever have to travel would be 3, and the maximum distance the other node would ever have to travel would be actually a full 6. So in this case, you end up getting a 3-6 dominating set instead of something smaller. So we will mainly be looking at 2-3 dominating sets here, and we will specifically be looking at them on paths. And so 2-3 dominating set, as you saw the one before, it's basically just your m value is, the m value is 2 and the n value is 3. There's the example again, and basically we're finding all the paths, like every single path that has a 2-3 dominating set, and we'll be finding the optimal set on there, which is to say the set with the least cardinality possible. So it can be a little difficult. It can be very difficult to find whether a set is optimal or not, but we go into finding that in just a little bit. We've already seen the dominating set on P4, and one way that it would make it easier to tell whether we have an optimal set or not is to know what the least cardinality is, because clearly if the lowest cardinality you can have is something, then, and you have that, then it's definitely optimal. We already know this for P4, just because as we see here, the least cardinality possible for P4 in this case for 2-3 dominating set would be 2, and since you have to have at least 2 guards to be able to have a secondary dominating set in the first place, then you're definitely going to have an optimal set on P4 here. So next thing we'll look at is optimal dominating sets on P5. We don't want to just look at P4. We should try and find all of them. So we have multiple arrangements of the sets here on P5, and in fact these are both optimal because they both are 2-3 dominating sets on P5, and they both only have 2 elements, so they're both optimal. We'll use the upper way of displaying it simply because it's much more useful later on. For now, these are still, there can be more than one way to rearrange. This just shows there can be more than one way to rearrange the set on the path to be able to have an optimal dominating set. Another one to look at is P6, and it's easy to see that this is a 2-3 dominating set, so because 2-3 and 2-3 on that end. And this one's a little different. All the ones we've seen so far, they end with a guard at the end, and this one ends up in open. There's no guard at the end. So it seems like it's just a little. It just seems different, and there is actually no way to get a representation with only 2 guards that ends in guard. So this is the only one possible for an optimal 2-3 dominating set. And of course, since there are only 2 elements in the set and there have to be 2, it's optimal. Optimal dominating set on P7, we can see this is 2-3. It's a little different than the ones we've looked at so far, but overall the maximum distance the closest after travel is 2, the maximum distance the second closest guard after travel is 3, so you still get a 2-3. We can't yet see that this is optimal though. It's like, because it has 3 nodes, 3 guard nodes, and it's not, we don't have any material yet that says, well, this one must have 3. All we know is it has to have at least 2. So we'll be showing that in just a little while. First thing we're going to need to be able to show that is something called the optimal distance. And the optimal distance will be the maximum number of nodes that can be between 2 guards where the gamma 2-3 relation is maintained. So basically you have a 2-3 dominating set on a path, and this is the max, for the 2-3 dominating set, this is the maximum distance the two guards can be apart. We can find this, the optimal distance, by trying different paths. If we look at P5, for example, we know that it has 3 guards. In one of the ways that we displayed it, it has 3 nodes between the guards. And we still have to wonder if you can have more and still have a 2-3 relation. So if we try it with 4 nodes in between, we end up getting this representation of P6, and this is not a 2-3 dominating set. So there's no way you can have more than 3 nodes between, and so we can tell that 3 will be the maximum between 2 guards. So our optimal distance here would be, for a 2-3 dominating set on paths, would have to be 3. This is basically for all paths, the optimal distance between 2 guards would have to be 3. If we notice the optimal distance used it's used in P5 basically, and you can see we know that's actually optimal already. So we can tell that by having an optimal distance between 2 guards, we can get an optimal set locally. So every section of that would be an optimal set, or an optimal set. Another thing I'd like to introduce is the fully optimal. And basically, if you have a fully optimal path, it's a path in which the distance between every guard is an optimal distance. So basically, imagine a whole bunch of P5 sit right next to each other. We have an optimal distance at every local area, and so it would always be an optimal set there. And a fully optimal set is the set containing all of those guards in the fully optimal path. In terms of 2-3 dominating sets, there are 3 nodes in between each 2 guards, as we said before. This could, of course, be different if we were talking about different dominating sets. And the last thing is that we like to look at is add-ons. Basically, we can construct a basically what we call add-ons are small paths that you basically compose with your previous paths, and you can basically extend our previous paths. The 2 here are a little different. The first one is basically the optimal distance. You already have the 3 nodes there, and you expect a guard to be right at the end on the other side. The second is actually more of a specific one for P6, extending P6. P6 is a little bit different because it had no guard at the end, and so you need to make a way for you to have an optimal distance there. A good thing we can do is use the first add-on with P5 to create a fully optimal path. So if you take P5 and you extend it with add-on 1, you end up getting a path of this size, 5 plus 4R, and R is just the number of add-on ones you use. Our purpose for having add-on 2 is to correct the extension of P6, as I said before. And P6 does not end a guard, so we cannot use add-on 1 or like right away, or we will not be able to get an optimal set on that path. So we need to figure out a way to find the optimal distance between those sets of guards. The way P6 is designed, you have 2 guards right next to each other in the middle. And so if we were to say add on 2 to P6 to the right side of P6, we would get something like this on the right side. And this on PA, you can see that it's still a 2-3 dominating set, And the question we have again is whether we can extend that and have more nodes in between. So we have P9 here, and we try to see if that works, and this is not a 2-3 dominating set on P9. So we realized that we would have to use something like P8, the one on P8. So our optimal distance for this part would have to be 4 nodes between. If we use add-on 2 for P6, we get a path ending in a guard now. So we're at P10 now, and we have a guard at the end, and so from there on you can use add-on 1. The main question still is would P10 at that point be optimal? But we can still find that because the optimal distance is 4 for those, and we'll find a better proof of that later. The main way we can produce paths in between sizes of R and R plus 1, saying you have R add-ons or R plus 1 add-ons, and the original 4 paths we proved have optimal 2-3 dominating sets. So we can tell if these paths are optimal using the fully optimal path that we discussed earlier, which would basically be P5 extended with add-on 1s. We don't have enough information we do actually have enough information now to prove that P7 is an optimal 2-3 dominating set, or there's a 2-3 dominating set on P7. We already showed this 2-3 dominating set, and what we need to know now is how many guards, or how many elements can be in the set how many elements have to be in the set for it to be a 2-3 dominating set. And so the fully optimal set will have a certain number of elements based on the size of the path, and so the number of guards for the size will be 2 plus R. Basically, you can see that if you look at P5, and every time you're adding 4 new nodes and a guard. And so every time you're adding 1 guard to it, so you usually have 2 guards, you're adding 1 for every single time you add. We know there can be multiple arrangements of paths, like in the original 2 from P5 that we saw. If we add between 1 and 3 nodes with a guard on, if you have a path that has a guard on the last node, and you add between 1 and 3 nodes to that, you will get you'll still have an optimal set if you have a guard on the end. Basically because there can be multiple arrangements of that, and you can't have, up to that point, there's 1 less than that. You can't continue on from there, as we saw from the optimal distance. So you have paths between R and R plus 1 must have the same number of guards as P5 plus 4R. By using the add-ons and P7, we end up having 3 plus R guards. Basically, you can see that there are 3 guards in P7. Every time you add on, you have an extra guard. When R equals 0, P7 has 3 guards, and so does P8. So we have an optimal. We end up having an optimal set because 5 plus P are 4. So now really what we need to do is generate larger paths, and the way it's been noted so far, 4 plus 4R, 5 plus 4R, 6 plus 4R, and 7 plus 4R is basically the formulas for creating, or what the path size would be. And R will be the number of add-ons, of course, and so 4R corresponds to how many add-ons you have, and 4, 5, 6, and 7 are the original P4, P5, P6, and P7. The number of guards for these are pretty normal for 4 and 5. So 4 plus 4R, you get 2 plus R guards for that, and 5 plus 4, you also get 2 plus R guards. With P6, since it's a little bit different, we end up getting when R equals 0 or 1, you end up getting 2 plus 2R. Since there are 2 guards in set, in the first one you have to use add-on 2, so you would get an extra 2 guards. When R is greater than 1, you end up getting 3 plus R because it goes back to the standard format, and you're adding add-on 1s at that point. Main question is, do all these paths have optimal 2-3 dominating sets? Because that's what we're looking for. And all these paths generated in these formulas have 2-3 dominating sets. We found they originally have 2-3 dominating sets, and when you add on the optimal distance, you still have another optimal set at the end, or another 2-3 dominating set at the end. So the entire thing is still going to be a 2-3 dominating set on whatever path it is. We also end up getting every path as a 2-3 dominating set. Basically, what I mean by that is 4 plus 4R. Basically, you'll get P8 right after P7, and then from there you'll get P12 right after P11, or et cetera, et cetera. We claim that all paths generated have optimal 2-3 dominating sets. Basically, there are 4 cases, and what we denoted here was the first case would be for 4 plus 4R for the P4 set, and you have 2 plus R guards, 2 plus R guards. It's always going to be the same because it comes right before there, and every single time it's going to be right along with it. So as long as it has the same amount of guards as P5 plus 4R, then it'll be absolutely fine. P5, we get the fully optimal path, so we already know that this is actually optimal at all points. And in case 3, you also have the 2 different parts of when R equals 0 and 1, and also when R is greater than 1. And we end up getting the same number of guards there. Same thing for case 4 when we talk about P7. One of the main things that is very interesting about this is that the applications that we can use for it. There are a lot of things in strategic planning that you can use, such as you have a long stretch of road, and say you have multiple different fire stations or police departments or guards of any kind. We want to be able to have them a certain distance apart where they can respond accordingly, but we also want them to we don't want to have too many of them because that brings up cost, and that also is just inefficient. Can also be used for different things in city planning, basically planning overall. It's very useful. Things in the future I would actually like to work on would be generalizing formation. So I wasn't sure if it could quite be done or not, but just an overall formulation of different paths and being able to find optimal sets on them, just for M and N instead of just specific 2, 3. Another thing I would like to actually look at other types of graphs. I don't want to just look at paths necessarily. It would be more interesting maybe to look at trees or different other types. We could also look at what I was thinking would be kind of cool was the possibility of, say, 3rd domination instead of just secondary domination. I'm not sure if anything has been done in that at all, but it would be interesting to look at what would happen in that situation. All right, that's it.
We have time for a few questions.
I have a question, a couple of them pretty quick. You mentioned